Hello, I'd like to welcome you to the first of our Fireside chats that accompany our course on experimental design on Coursera. Um, I'm looking forward to these opportunities to exchange some conversations with you. I want to start off by thanking a lot of people that made this possible. This is not just me sitting in front of the fireplace. There's a lot of folks that have put great deal of effort into the course itself and into this production. Here at GOE, that's the Global Outreach and Extended Education Group in Fulton School of Engineering at ASU. Octavio, Scott, done a lot in terms of the management side of things. Dustin Hampton has done a fabulous job in developing this particular portion of our course. I need to thank Carly Metcalf, who did the video presentations on JUMP and just I think did a fabulous job with that. I hope you'll find those to be really useful. And I'm planning to have Carly as a guest on an upcoming Fireside chat, so you get a chance to meet her. She's really sort of crunching away trying to get out of here. She's my PhD student, and she's almost done with her dissertation, and she's accepted a job at RIT. And so she needs to get finished, and so her motivation is pretty high right now to get done. But she said she would like to come, and so I'm planning to have her as a guest for the Fireside chat. I also owe a lot of gratitude to Amy Kitchens, who's one of the course developers here. That she took a lot of really strange, unusual, probably bad ideas that I had, and turned them into a lot of really useful supplements for the course, things like learning objectives and problems, and she just did a really great job. And Megan Gibson, who also is part of our organization here, has done a great deal of work in terms of promoting the Fireside chats. And she's actually in the studio, and she's one of the people that I'll be interacting with during the course of the Fireside chat. Okay, just a couple of reminders about how we're going to do this. Megan said that I should refer to them as etiquette reminders. This is pretty common for Zoom meetings, I think. The mics and videos for participants are all turned off except for me. Please don't turn them on. But if you want to submit a question to me, please use the chat function in Zoom to do that, and that's on the Zoom menu bar. The way I'm going to run these Fireside chats is we're going to have some discussion from me about various things that I think you might be interested in. And then we are going to have a Q&A session. And depending on the number of questions, it may take me a while to get to your specific question. And sometimes the question might be complicated enough or require more information, either from you or from me, than I can easily do in a back and forth environment like this. And so we'll have to have some dialogue to find out a little bit more about what you want to know. And by the way, we are going to answer all the questions one way or another. If they don't get answered during this live session, then I'll deal with them afterwards, and we'll respond to that in Coursera. So I do encourage you to ask questions. I hope you will do that. And by the way, I hope you're finding the course interesting and enjoyable. A little bit of background, a little bit of motivation about the Fireside chat. Where did this idea come from? Well, it's not unique to me. I'm following on to President Franklin Roosevelt. President Roosevelt held Fireside chats on a regular basis with the American public, and he did them via radio from 1933 until 1944. That's a long period of time. It's longer than I'm going to be doing a Fireside Chat, but he did it for 11 years. And over that 11-year period, he did about 30 of them, as near as I can determine. My parents were young adults during that period of time. I was born in 1943. And they remember the Fireside Chats. In fact, as a kid growing up, I can remember them telling me that, oh, well, we used to listen to President Roosevelt doing the Fireside Chats. So I've known about Fireside Chats for a long time. Initially, in the early years of the Fireside Chats that Roosevelt did, he was trying to explain his policies, and he was trying to explain what he was trying to accomplish in his presidency. Now, you probably remember, a lot of you will certainly remember, that this was an era of what we call the Great Depression. The stock market crash in 1929 led to massive unemployment, businesses and industries failing. It was a terrible situation. And it has some parallels to what's going on right now, of course, with the coronavirus pandemic. But much worse. And so Roosevelt was trying to explain to the American public his ideas, what he wanted to do to try to get the country going again, to get the world going again, because it was a worldwide depression, not just in the U.S. And this was, of course, the origin of what has become known in American history as the New Deal. And out of that came some really remarkable things. Probably the one that has the most lasting impact for most Americans is Social Security. Social Security did not exist in 1929. And Roosevelt was able to push the idea of Social Security through Congress and make it work. And the Works Public Administration, the WPA, built parks and highways and roads and dams all over the country. We have a park here in Phoenix, the South Mountain Park, that was a WPA project during the 1930s. That's where this wonderful South Mountain Park that we have. I live adjacent to South Mountain Park, and it's a wonderful place, and with horse trails and hiking trails and bike trails and just all sorts of interesting things, and lots of wildlife. I routinely see coyotes and javelina and all sorts of other creatures, including rattlesnakes, around my house, simply because this wonderful park is there, which would not have happened if it weren't for Roosevelt and the WPA. So in the beginning, these Fireside Chats were a way to communicate what he hoped were positive things that were going to go on in the country. And of course, they continued into World War II. And the Fireside Chats in 1942 and early 1943 were more about the war and about war news. And of course, the war in 42 and 43 was not going very well. It was not until about the middle of the early part of 1943 that the war began to turn around with things like the Battle of the Coral Sea and the Battle of Midway in the Pacific. I'm a naval historian by hobby, and so I know a lot about World War II and particularly the war in the Pacific. And so he did a lot of things to encourage and motivate people to think about the positive aspects of what was trying to go on during the war. He did about 30 of these, I think I mentioned. They lasted up to about 30 minutes. Maybe some of them a little longer, some of them a little less, but they were aimed at 30-minute conversations. They were said to be wildly popular. The estimates that I have read indicate that about 70% of the adults in the United States listened to at least some of those Fireside Chats. And I can remember my mom and dad saying that they really didn't want to miss any of them. So they were very, very popular, and I hope this will be just as popular with you. Okay, a couple of things about the course, and then we'll move on to maybe some questions. But one of the things I do want to talk about the course, a couple of things. I think the lectures are very helpful in terms of understanding the material. I think the jump video demos that Carly did are extremely good, and I urge you to watch those along with the lecture material that I've put together. I hope that you will also look at the textbook that's recommended for this course. This is the 10th edition of my Design of Experiments book, and I'm strongly suggesting that the ebook would be the way to go. This book has been around a very, very long time. I wrote the first edition of it in the 70s. The first edition was published in 1976. And the reason I wrote the book is because I was teaching experimental design in the engineering school at Georgia Tech in the 70s. And there really weren't any textbooks that were suitable for an experimental design course for people in engineering and science and other fields other than agriculture. There were a couple of really great books on experimental design that were really devoted to ag science applications. And I was using one of those, a great book by two people, William G. Cochran and Gertrude Cox. It was really a great book, but it was all agriculture. And I got really tired of going into my classroom at Georgia Tech full of engineers and say, okay, well, we're going to talk about an example today. And what do you do if you have 4 sheep? Well, you don't get good answers to that in most cases. And so I set out to find good engineering examples. And it was not hard to do that at Georgia Tech. All I had to do was go knock on the doors of most of my colleagues and say, I understand that you have a research project that deals with X. And do you do experiments? And of course, the answer was, sure we do. And would you like some help? And at first, they were a little suspicious as to what sort of help I might be able to provide. But word got around pretty quickly that I actually could be useful. And so I began to develop a lot of really good engineering and science examples of experimental designs. And that was the basis of, first of all, improving my course so that it was more meaningful to the students. And secondly, it was the origins of the book. And since the book came out, it's been through numerous revisions. As I say, the current edition, which is 2020 this year, is the 10th edition. People keep kidding me. They say, well, what are you doing? Are you doing it over and over again until you get it right? And by the way, that works well in a lot of things, doing it over and over again until you get it right. You want to know how to get really good at any one thing? Do it about 10,000 times. That's how you get good at something. I played a lot of golf in my life. I don't play anymore because I have an arthritic shoulder, so that's gone. But I played a lot of golf, and I floated around about an 8 or a 10 handicap. So I was a pretty good player. I was not going to embarrass myself. I was not a naturally gifted golfer. The way I got to an 8 or 10 handicap was when I was a kid. When I started playing golf, when I was about 8 or 9 years old, I hit a lot of practice balls. There were years that I hit 10,000 practice balls. Okay, so if you want to get good at something, do it a lot. Okay. And that's why I suggest watching the videos, paying attention to them, looking at Carly's fabulous examples, and reading the suggested material in the textbook. The textbook has a lot of interesting features, things that you could do with ebooks that you can't do with paper books. For example, in the ebook, there are suggested homework problems. And many of those homework problems have built-in solutions. So if you just click the little solution icon in the ebook, the solution pops up. So that's very useful if you're really trying to take ownership of the material by working some of the problems. There are also some supplemental videos in the book that you can access just by clicking on the video link. And they are, in many cases, things that, in fact, I would say in all cases, there are things that we're talking about in the MOOC, in the lectures, but they're often done a little bit differently. They're done in a little different way. You're maybe hearing something that is similar to what you heard in the MOOC, but it's done a little differently. It's done a little different way, and that can be enormously helpful in terms of taking ownership of the material. There's also a lot of supplemental material in the textbook. Back in the days when the book was completely paper, the publisher, who by the way has been wonderful to work with, they would harass me about putting too much material in the book and making it too long. They were concerned about killing too many trees, I think. Plus, they also were trying to keep the price of the book down. And the way you do that is you keep the page count down. So I produced a lot of this supplemental material as Word documents, and they were on the book's website for many, many years. Well, now all that supplemental material can be accessed in the ebook. All you have to do is look at the title of some supplemental material and click on that title, and it will open up the original Word document that I wrote, and you can use that however you would like. I wrote it as a Word document, so you could copy it, you could cut it, paste it, you could do whatever you wanted to with it. It's yours to use in any way that you find helpful. I think some of the supplemental topics are extremely beneficial. For example, in chapter 1 of the book, one of the things that we talk about, and I hope you've all looked at the lectures for the first course, or at least read chapter 1. One of the things we talk about is a process for planning and conducting experiments. This is a really important set of material. Well, in addition to the material that's in the book and on the video, in the supplemental material, there's a great deal of additional discussion of this topic, along with other references and some example application ideas that I think you would find very, very useful. A lot of that is extracted from a journal paper that I wrote back in the 90s with a colleague from Alcoa, one of their research engineers named David Coleman. And David and I had done a lot of work together. I did a lot of consulting for Alcoa over the years. And we realized that the planning process was really important. And so David and I wrote this article, which appeared in Technometrics, a stat journal. And in that article, we actually suggested a series of worksheets and guide sheets that could help you in planning experiments. And they're illustrated in the supplemental material. And so I would think that you would actually find that really, really useful. Okay, one thing I do want to talk about a little bit more before we get to the question part and answer part of the Fireside Chat is I do want to talk about that section in chapter 1 on planning and conducting experiments. This is a really important set of material. Even if you're a knowledgeable authority on running experiments, I think reading this would be, and thinking about this, and even looking at the supplemental material that accompanies this, would be beneficial. And by the way, in that supplemental material, there's references to some other papers about planning experiments that are very, very good. But that is a 7-step process. If you look at the textbook, it's a 7-step process, and all of the steps are pretty important. One of the pieces of advice that I always give to my students is that here's how I think you should go about doing this. And this is not really original to me. This suggestion came from a professor at Purdue University many years ago, Charles Hicks. He was a math and stat professor and taught a very, very good, very popular course on experimental design at Purdue. And he used to tell his students that if you had 10 weeks to solve a problem with an experiment, you should spend 8 weeks planning it, 1 week running the experiment, and 1 week analyzing the data. So what do you take away from that? Okay, what do you take away from that? What I take away from that is that planning is crucially important, and that it's 80% of your success. If you do a good job of planning, things will evolve in a pleasant and useful way. If you do a bad job of planning, the ship may be sinking. Okay, so something to keep in mind. There are a couple things about that process that I do want to mention. One of them is very important, and that's the actual conduct of the experiment itself. It is so easy to think that this is a simple process and that nothing can go wrong. But you really, you can't overestimate the sorts of disasters that can happen to you in running experiments. Here's one that I've seen quite a few times, okay? The experimental material has to be moved from one tool or one position on a tool to another. This happens a lot in, for example, semiconductor manufacturing, where you're moving wafers, say from a tool that deposits material on the surface of a wafer to an etching tool. Okay, so you're moving these wafers, and somebody drops one of them, and they break it. Okay, so your lot of test wafers maybe had 20 wafers, and you've already planned to use all of them in the experiment. So you're stuck. You've lost one of the runs in your experiment. Terrible. How do you prevent this kind of thing? Well, one of the ways to prevent mistakes in any kind of activity is called practice. What do baseball teams do before the season? What do football teams do before a game? What do? They practice, okay? That way they don't make mistakes. So if there are handling operations and operations that require some degree of skill or dexterity, make sure that the people that are going to be doing that know how to do it, and they've done it in practice to make sure that they don't damage or destroy or break specimens. I've seen this over and over and over again. Another aspect of that is traceability. So now you've successfully run the experiment, and you've got all the experimental units, all the material together, and you have to send it off to an analytical laboratory to have some measurements done, okay? How do you keep track of those units? You better find a way to do that, because laboratories have been known to lose your experimental material. They've been known to damage it. And that causes complete disasters. I remember one experiment years ago, and in fact, the individual who was running this experiment is now a colleague of mine here at ASU. He ended up coming to school and doing his PhD with me, but he was running an experiment in a wafer lab. And this was a high priority, high profile experiment for a key customer. And they literally shut down the factory to be able to run his experiment. It took a week to do it. They got all the experimental material finished by the end of the week. And the analytical lab people said, all right, I'm going to bring my crew in over the weekend on Saturday, and we're going to have all the analysis done. You will have everything first thing Monday morning. So a colleague of mine, he goes in first thing on Monday morning, and he can't find the report from the lab. And it's kind of worried. It's like 6 in the morning. He can't find it. He says, well, maybe it's not here. So he starts looking for the wafers. And he can't find them anywhere, not in the lab, not in the fab. So he's kind of getting a little worried, and he finally runs into one of the fab managers, the factory managers. And he says, Fred, where are my wafers? And he said, what wafers? He says, well, the ones that were on that cart right outside my office. He says, oh, those wafers. You know, we did a preliminary QC check on those, and they all looked pretty good. So we shipped them. They shipped them. They put them on an airplane and sent them to the assembly site in Korea. So those wafers are over in Korea being sliced and diced and mounted on printed circuit boards to send to the customer. So it's not a case of having one of your experimental units lost or broken or missing. Every single one of them was lost or broken or missing because they didn't maintain good traceability of the parts and good identification of the parts. You think these kind of things are silly and stupid, and they shouldn't happen, but they do. They happen a lot. And there are other simpler mistakes that go on all the time. One of my favorites is no one on the team is assigned to make sure that all of the factor levels are adjusted to the proper level before the run is made. And invariably, when you don't do that, somebody forgets to change one of the knobs on the tool. And so you get a run that's now made without the proper setting for at least one of the factors. And usually that ends up producing a really strange answer that doesn't make any sense, and you don't know what to do with it. So somebody should be responsible for making sure that all of the levels of the factors are correct before you do a run. Simple. Another issue that is a problem is randomization. In the course, I talk a lot about randomizing the order of the runs, okay? Why do I talk about randomizing the order of the runs? Well, because randomization is essential to statistics working properly. Statistical methods, in order to be valid, have to be working with a random sample from the population. And if your sample isn't random, the results are likely to be erroneous. In fact, they will probably be erroneous. Getting a random sample is not always easy. It sometimes requires some effort, but getting a random sample is really key and really important. And by the way, it's one of the things that we're seeing right now in the U.S. with testing for coronavirus. And we're seeing that percent positive rates vary all over the place with the number of tests. Well, I think you have to look at some of that data very carefully, because are those tests being administered to a random sample of the population? Well, probably not. A lot of testing is self-selective. People are deciding they need to get a test, and so they go get one. Sometimes the tests are focused more on potential at-risk populations, like patients, residents of nursing homes and extended care facilities. So you have to be a little bit careful. The sampling is probably not random. If it was really widespread, hundreds of thousands of tests, you might be able to suspect that maybe they're dealing with random samples. I have a great example for you of where failing to get a random sample caused a really huge mistake, okay? You're gonna love this because it's about an election, okay? And of course, we're in an election year, okay? So this is the presidential election of 1936, okay? I don't know if any of you were alive in 1936. I wasn't, but my mom and dad remember this election quite well. So let me tell you the story of the 1936 election. The two candidates were Franklin Roosevelt, who was running for re-election, okay, and Alf Landon, who was the Republican governor of Kansas. And the Landon family is quite famous in politics. In fact, for many years, his daughter, Nancy Landon Kestenbaum, was a senator from Kansas, and she served notably and honorably in the Senate for many, many years. But Alf Landon was the governor of Kansas in 1936, and these two candidates had really different ideas about how to fix what was going on in the country at the time, which of course is the Great Depression. Roosevelt is pushing the New Deal. Landon is sort of looking for a less government intervention, more austere kind of approach to dealing with things. So these two candidates were pretty different. They were pretty different, about as different as you could get. Well, what's the story? Well, in the 1930s, there was a magazine published in the United States called the Literary Digest. Now, that is not to be confused with the Reader's Digest, which is a completely different publication in later years. But the Literary Digest was a moderately popular, sort of upscale magazine that was published for quite a few years. And they decided in that election year that they would conduct a presidential preference survey. Wow. Now, we're used to surveys, right? We're used to that sort of thing. They go on all the time. You can't have an election for dog catcher in the US without having a poll or a survey taken to see who should be elected or who we think is going to be elected dog catcher. Okay, so we've gotten used to survey polling, survey sampling, as it's called in the statistics world. Well, in the 1930s, this was not anything that people routinely did at all. So this was kind of a new thing for the folks at the Literary Digest to take on. So they did. They prepared and sent out, now hold on to your chair, 10 million ballots. 10 million ballots asking who are you going to vote for, Landon or Roosevelt. That is an enormous number of ballots. They got back 2.4 million responses. So the sample size, N, is 2.4 million. You ever heard of a contemporary poll or survey with a sample size of 2.4 million? I don't think so. Mostly the sample sizes are in the few hundreds or a couple thousand. This is astounding. 2.4 million. Okay, when they analyzed the results, the respondents indicated that 53% of them were going to vote for Landon and 47% of them were going to vote for Roosevelt. Interesting. And so they published the results and they said, Landon's going to win. Okay. What actually happened? Do you remember, or do you know from a study of history? Well, of course you know. Roosevelt won, but it was a pretty widespread victory. He got something like 65% of the vote. So instead of 47%, he got like 65% of the vote. They missed the percentage of the vote that he was going to get by 18 or 19%. A complete disaster. And how on earth could they have made such a crazy mistake? How could that have happened? Because the margin of error on the percentage of people that are going to vote for a particular candidate is 1 over the square root of n. Okay, it's proportional to 1 over the square root of n. Well, 1 over the square root of n. Now remember, n is 2.4 million, okay? If you look at 1 over the square root of 2.4 million and express that as a percent, it's 0.065%. It's 0.065%. That's the margin of error. Less than 1%. Isn't that astounding? And they missed it by 18 or 19%. So what's going on here? Well, one of the things that an authority on survey sampling would talk about is something called the reporting bias. You only got 2.4 million replies. Okay, so there's 7.6 million people that didn't bother to reply. So selection bias is perhaps a non-response bias is perhaps a problem. Okay, and we recognize that. But the other maybe more serious problem with this is, where did they get the 10 million names? Well, they started by selecting some names at random now, mind you, okay, from their subscriber list. Well, they didn't have anywhere near enough subscribers to be able to come up with 10 million names. So the next thing they did is they chose telephone books from around the country, randomly chosen from around the country, and they randomly chose names and addresses from telephone books. Okay, and then they made up the rest of the 10 million names by choosing names at random from the membership lists of business organizations, professional societies, and social clubs. Wow. All right. Do you see what the problem might be here? It's 1936. Okay. There's a depression going on. Who has a telephone? Well, not everybody. In fact, telephones were kind of a luxury. You had to have some spare change to have a telephone. My mother was a telephone operator in the 1930s. And she belonged to an organization called the Telephone Pioneers of America. And so I asked her to do a little research for me. And I said, Mom, how many people actually had residential telephones in 1936? And she did a little research and discovered that there were fewer heads of household that had telephones than there were heads of household that were unemployed. There was something like 20 million heads of household unemployed and fewer than 20 million residential telephones. Amazing, amazing. Who belonged to business organizations, professional societies, and social clubs? Well, it was people that had money, disposable income, because that's how you pay the dues for those organizations. People that were employed. The sample that they had was so non-random, it's ridiculous. And it was skewed toward the upper income, more financially secure segment of the population, who are more than likely not all as excited as the average person suffering in the Depression was about the New Deal. So here's an example of a non-random sample that produced a disastrously wrong answer. In this case, all the non-random sample did, this huge non-random sample, all it did is it enabled you to calculate the wrong answer to a higher level of precision, a level of precision of about 0.065%. Ridiculous. Okay, so make sure that you have a process for getting a random sample. Now, as you go through this process of deciding how to run your experiment, you're going to run into complications caused by random sampling. For example, some variables are harder to change than others. And so if you have to change a variable like temperature, and when you change the set point on temperature, if it takes your process 30 minutes or an hour to stabilize at the new temperature, that adds time and adds a cost and complexity to running your experiment. So you may be tempted to short circuit this and maybe not change temperature randomly. Instead of having to change the temperature 8 times, maybe you say, well, I'm only going to change it once. I'm going to do all the low temperature runs first, followed by all the high temperature runs. This is a really bad idea. Okay, this is a really bad idea. Don't do this. There is a technique that we will talk about in the course called the split plot design that is, it's set up to help you deal with these hard to change factors. So don't throw in the towel and start monkeying around with the random test sequence. We're gonna get around to showing you how to deal with hard to change factors in the course. It's part of the material that we cover in the last course. Okay, so that sort of ends the material that I had planned to talk about in our first Fireside chat. And we've got about 15 or 20 minutes left, and I'm going to try to deal with some of the questions that have come in. And Megan is taking your chat questions and projecting them for me on a screen, and I'm going to read them so that you'll know what the questions are. And this first one is a really good question. It says, can you elaborate on the Plackett-Burman design, including its strengths and weaknesses, and is there another similar design? Well, Plackett-Burman designs are examples of fractional factorial designs. The most well-known version of these are all two-level designs. That is, all the factors have exactly 2 levels. And the number of runs in a Plackett-Burman design is either a power of 2, okay, or a multiple of 4. Now, of course, powers of 2, turn out to be multiples of 4, but there are many multiples of 4 that are not powers of 2, such as 12, 20, 24, and so on and so forth. And so those are the designs that we think of as being the most useful or the most interesting in the Plackett-Burman family. The Plackett-Burman designs, where n is a power of 2, they're the same as the standard 2-level fractional factorials. But the Plackett-Burman designs, which have 12 runs, 20 runs, 24 runs, 28 runs are a multiple of 4. They are different designs because they have different alias relationships. In these designs, there is partial aliasing of main effects and 2-factor interactions. They are resolution 3 designs, but that is main effects, alias of 2-factor interactions, but the alias structures are not complete. In other words, the main effect of A, for example, in a 12-run Plackett-Burman design is aliased with every 2-factor interaction that does not include A. So A would be aliased with BC, BD, BE, so on and so forth. That design has 55 2-factor interactions. 45 of them are aliased with the main effect of A. And in fact, 45 2-factor interactions are aliased with every one of the 12 main effects in that, every one of the 11 main effects in that 12-run design. What's the strength of these designs? Well, the strength of these designs is because the aliasing is not complete. And so with a small design, you may be able to estimate both main effects and get some information about 2-factor interactions, which you wouldn't be able to get from a standard resolution 3 design. So this is a great potential strength of the Plackett-Burman design. The weakness is that because of this aliasing, if there are a number of strong 2-factor interactions, it may be difficult to completely untangle these experiments, these effects. So that's, and methods for analyzing them there's a variety of methods, and different methods can produce different results. Are there other designs similar to Plackett-Burman designs? And the answer is yes. Plackett-Burman designs are a member of the class of what we call non-regular fractions. Non-regular fractions are fractional designs where the alias relationships are not complete. That is, the aliasing between, say, main effects of two-factor interactions is not complete. The correlation, if you will, is less than 1. There's a whole family of non-regular two-level designs. Some of those are discussed in the book. And in the next Fireside Chat, we're going to actually talk about a place where these non-regular designs would be extremely useful. So more to come on that topic. It's a great question. I really enjoyed this. How can we deal with process operators? Sometimes they deny execution of the experiment as designed due to too many changes on process variables. Yeah, you're right. Getting the operating personnel on board is often tricky. Here's my advice. Designing an experiment is a team activity. Get the operating personnel involved at the very beginning so that they understand the problem, they understand the challenge, they understand the importance, and get them to buy in early on. Let them make suggestions about which variables to use and which variables maybe to not change in a particular experiment. Getting buy-in from the operators is really important. If you don't do that, I've seen examples where the operators basically shot your experiment down by not executing it correctly. Okay, another question. Sometimes we have repeated measurements of the same sample that come from a specific treatment. I understand that the variability in the repeats gives you an idea of the variability in your measurement method. During the course, most of the time, I see that there is only one observation per replicate in each treatment combination. My questions are these repeated measurements really a need? And also, when you have access to this information, how can you include it in your analysis? You have to average the repeats or include them separately? Good question, because there are places where we do get repeat measurements. It's the same experimental unit. The treatment combination was run only once, but we get 5 observations out of that. Maybe we have a part that gets measured in 5 different locations, or a part that gets measured 5 times. I think that you have to be careful about using that as experimental error, because it will tend to underestimate the experimental error. However, that information is useful because it can give you information about variability over that experimental unit. Now, that variability over that unit might be caused by measurement error, but it might also be caused by something going on the experimental material itself. For example, in semiconductor manufacturing, it might be, let's say, a layer thickness, variability in the thickness of a layer that's been deposited on the wafer. So these measurements can be useful. I think one of the things that you can do, well, first of all, if I'm really interested in experimental error, I typically tend to average the repeats, okay? But on the other hand, I think analyzing the variance or the average of those measurements across all of those repeats can be extremely useful. It'll give you an idea about another source of variability, that is the variability within the actual experimental material. If you look at the textbook, there is an example of this. I believe it is in chapter 6, but if you'll take a look at that, you'll see that there is an example there of a process where there were repeat measurements made, and we ended up analyzing both the average of the measurements across those repeats and then the variance. So, and by the way, when you analyze the variance, you almost always need to use the log of the variance instead of the variance itself, because the variance has a very non-normal distribution for small sample sizes. But the log transformation usually makes it work pretty well. Good question. When I went to the laboratory, the operators were doing the experiments in the order they wanted. Oh boy. Another problem of R&R is an operator thinks they are being evaluated and become afraid of being fired. How do you deal with this? Get them involved. Get them involved in planning the experiment. Get them involved in the design, understanding the importance of what they're doing, and if you need to have the sheriff in the lab to make sure that they are running the experiment in the proper order, then do that. But I don't like to do that. I think you want to get them on board, and this whole thing about fear. This is Deming talked about this, and it's so important. Organizations have to try to drive out fear. Read Deming. He talks about this a lot, and this is part of corporate culture that I think we have to make this go away. But getting the operating personnel involved is in the actual planning of the experiment, and understanding why randomization is so important is really critical. Good question. Can you elaborate more on graphical presentation of observations, and can you share some tips? Well, I think I mentioned somewhere in the course that the very first thing that you should do is plot the data. Yogi Berra once, the great New York Yankees catcher, once said that you can learn a lot by just looking, or you can see a lot by just looking, and that's certainly true with experimental data. Excuse me, I'm having allergy problems today. There are a lot of ways to plot data. I think box plots by factor level are useful. Box plots of observations within cells where you have replicates. Box plots that show you the differences between replicate 1 and replicate 2, replicate 3. These are all useful ideas. The type of graph that you use is dictated to a large extent by the type of test or the type of experiment that you've run. And I think this is a place where you can be really very creative in terms of displaying the data. Many computer packages, JMP, for example, has excellent graphical capability to portray data. And I strongly suggest that you explore the options that you have in JMP to help you do this. Good question. What's the most challenging experiment you've ever conducted? Did you get the intended results? Well, there have been quite a few of them, okay, but the one that was the most nerve-wracking for me was an experiment involving investment casting of a very large nickel titanium component. This nickel titanium component is a one-piece unit that forms the combustion chamber of a jet aircraft engine. These parts have to be perfect. The manufacturer was having problems with interior cracks and interior voids, which can only be seen on X-ray. These parts are very expensive. One test to produce one part could cost as much as $100,000. We needed to run an experiment with about 7 or 8 factors to be able to understand the investment casting process and see if there were factors in that investment process that were leading to the occurrence of these defects, these cracks. And by the way, they didn't happen very often. So this is another thing that made this experiment very complicated. We ended up using a 12-run Plackett-Burman design with 8 factors. Wow. Over $1 million, this experiment cost over $1 million to run, okay? When we got the results, by the way, the only way you can measure the results is either with X-ray inspection or with some sort of surface penetrant test. And the X-ray inspection is very subjective. Is that a crack or not? Or is that a void or not? Yeah. So we ended up developing a measurement system that was based on forced ranking of the parts. The best one is number 1. The next best one is number 2. We'll talk more about this kind of response variable later because it's going to come up again in an example I'm going to show you in the next Fireside Chat. Well, happily, we got good results. We were able to discover there were certain factor levels, such as the speed of the investment, the casting temperature. There were factors that were really critical to this defect formation process. And fortunately, the results of the experiment did point to a way to improve this process and make these defects go away. This is a good question. Suppose you have a catastrophe and you lose one of the runs. What do? Should you repeat the whole experiment? Well, a lot of times you don't have the resources to do that. Can you just do another run? Well, if you still have the same experimental material, for example, if you don't have to go into a new batch of material to do this, you probably could do that and just consider it to be a part of the same block. It may not be easy to do this, to repeat this lost run and treat it as a new block because it may not be orthogonal to the other factors. But what I often suggest doing is just don't include that run in your analysis. Most designs are very insensitive to losing a run or two. And so you can analyze the experiment with the data you have. Another possibility is to simply estimate the missing value. There are techniques for estimating missing values. So estimate the missing value, plug that in, analyze the data. Then analyze the data not including that missing value and look at the difference, if any, between the two analyses. That should give you some encouragement that the analysis that you have is correct. If you can, just do that run again without introducing material from a new source or other factors that might need to be a blocking factor, you should do that. But it often really isn't a way to make that new measurement a block very easily. And the last thing you should do is rerun the entire experiment. That's probably a waste of time and money. Okay, we have hit the end of today's questions, at least the ones that I'm going to be able to deal with, because we are out of time. And I really hope that you have enjoyed this. I have had a lot of fun doing this. I love to talk about experimental design. I could go on for hours, but you probably have better things to do. So we're done for the day. And Megan, do we have some unanswered questions? Oh, looks like we got to them all. Great. So think about questions, and we'll do some more of this next time. And I think our next Fireside Chat is in 2 weeks. So looking forward to doing this again. Hope you've enjoyed it, and have a good rest of the week.